Today we are having quiz at 5, sir.
Yeah, mine are at 6 o'clock. Okay, I thought you can have some leisure time. I have put it at 6 o'clock.
Okay, sir. So from 6 to 7.
Yeah, 6 to 7.
Okay, sir.
Okay, hello everyone. Good afternoon, all of you. And today we start with a quote by Denzel Washington. The chances you take, the people you meet, the people you love, the faith that you have, that's what going to define you. Right? So we are defined by all these things. That's why many times people say it is always better to have satsang. Okay, live with nice people who are positive thinking and who are having love in their hearts. So if you stay with them or if you spend time with them, you also will acquire those qualities, and you will be defined by others in the same way. Okay, and today is the birthday of the great Vinoba Bhave. He is advocate of non-violence and human rights, and he is also considered as successor of Mahatma Gandhi. And he says it is only when our life proceeds within bounds and in an accepted, disciplined way that the mind can be free. And he also says it is a curious phenomenon that God has made the hearts of the poor rich and those of the rich poor. So here, poor in heart means having no love in the heart, and rich in the heart means having abundant love in the heart. So the people who are rich in money, they will be poor in the heart, and who are poor in the money, they are rich in the heart. Okay, he is often called as Acharya, or in Sanskrit for teacher. He is best known for the Bhudan movement. He got more than 1,000 villages by the way of donation, and he gone for donation to the people. So because he is a person who can be relied on, who can be believed to be a good man. He is considered as the national teacher of India and the spiritual successor of Mahatma Gandhi. The Gita has been translated by him with the name as Gitai. Okay, Tai means mother, so means Mother Gita. He has also written the essence of Quran, the essence of Christian teachings, thoughts on education, Swarajya Shastra, and all. He is a great personality, and he was born today. And okay, today we continue that governing equations. We will enter into Navier-Stokes equations. And just we quickly revise the last class. So we have discussed about the limitations of fluid dynamics, about what is continuum, and the limitation of the velocity and the mass of the system. And it is a macroscopic approach. Newton laws should be valid, and we should be inertial frame of reference. All those things we have discussed in the last class. And we have seen various types of fluid flows. Okay, viscous flows, viscous incompressible, inviscid viscous, inviscid compressible, inviscid incompressible, like that we have seen. And we have seen what are the different sciences that deal with those. And then we have talked about types of fluids, and we have seen Newtonian, thixotropic, rheopeptic, and dilatant, pseudoplastic, all those things we have discussed about. Then coming to the mathematics side, so we talked about substantial derivative, the total derivative of a fluid is the sum of local derivative and convective derivative. If there is some change in the property of a system, it is due to the local changes and also due to the movement of the fluid. That is convective derivative. And we have seen velocity gradients exist in the flow, and velocity gradients have some physical significance. And we have seen that different combinations of velocity gradients, they represent linear deformation, angular deformation, rotation, and all. We have proved it. And then we have seen the significance of gradient, divergence, and curl. And we have seen the divergence of velocity is nothing but the rate of volumetric strain, and the curl of velocity is nothing but the rotation or vorticity. And we have seen that general movement of a fluid particle, a general movement of a fluid particle has a lot of components in it. So it constitutes translation in XYZ directions, and linear deformation in XYZ directions, and angular deformation in x, y, y, z, and zx planes, and the rotation in different planes. So it constitutes all of these components in a general movement of the flowing particle. And then we have talked about the stream function, velocity, potential. If there is a 2D incompressible flow, okay, we'll discuss about that. So if you take 2D incompressible, so we have seen that del dot V is equal to 0 because the volumetric strain is 0. And if it is 2D rotational or even 3D also, I will reduce it to 2D. So the general irrotational thing is del cross V equal to 0. For 2D, omega z is equal to 0. So when it comes to 2D, this will be dou u by dou x plus dou v by dou y equal to 0. This is dou v by dou x minus dou u by dou y equal to 0. And because of this, we define u is equal to dou psi by dou y and v equal to minus dou psi by dou x. Here sufficient suffix means derivative. Okay. So similarly, u equal to phi x and v equal to phi dou phi by dou x and dou phi by dou y. And so we have seen that if psi equal to constant, it is called a streamline, and phi equal to constant means it is potential line. Okay, and so across streamline there will not be any flow because velocity is tangential to streamline. So normal velocity to a streamline is equal to 0. So here, because of this, and also we have seen that dy by dx of streamline is equal to v by u, and dy by dx of potential line is equal to minus u by v. So that's why we have seen that streamlines and potential lines are orthogonal. Okay, some other things we can, because streamline, if you see, normal component of velocity is equal to 0 because velocity is tangential to streamline. Okay, so in a flow, any streamline acts like a wall. Okay, if I take suppose streamlines for like this, so every streamline acts like a wall, right? Because there will not be any flow across it, and two adjacent streamlines acts like a channel. So if I take this streamline and this streamline, it acts like a channel, right? So because whatever flow goes this way, same flow comes out. Okay, so nothing joins in and leaves out. Okay, so it acts like a canal-like thing. Okay, channel or a canal. And because of that, so we can see where velocities are large and velocities are small. By seeing the streamline pattern, right, you can understand where the flow is accelerating, where the flow is decelerating, where velocities are large, where velocities are low. And because of this, and velocity and pressure, they are inverse of each other. If there is more velocity, less pressure, less velocity, more pressure. So pressure variation also, we can easily understand how the pressure variation is. This is for an ideal flow, 2D incompressible irrotational flow, right? 2D incompressible irrotational flow means this is ideal flow. Okay, for ideal flow, because Bernoulli's equation holds good, and if there is no gravitational force coming into So pressure energy and kinetic energy, if one increase, other decrease. Okay, that is the way. So if you see here, wherever the streamlines are away from each other, the velocities are low because same mass is going through it's like a canal. So whenever the walls are close to each other, there will be more velocity because same mass is going through. And the streamlines are away from each other, the velocity, suppose if you see here in these areas, velocities will be very low. And the area here, right, in these regions, velocities are large. So here, velocities are low. So what happens here? The pressure is very less. And here, the pressure is maximum. Actually, this is nothing but, what is this point called as?
Stagnation point.
Stagnation point. One interesting thing, okay? So here, because the velocity is tangential to a streamline, we say streamlines can never, can they intersect?
No,
No, sir.
So we say streamlines never intersect, but there are 2 points where streamlines intersect. Can anybody tell me?
Sir, one is a stagnant point.
Stagnation point. Now you see, actually this is one streamline, and this is another streamline. These 2 streamlines intersect here. Okay, so stagnation point is a point where streamlines intersect. There is another point also called as singular point, right? So if you see source and sink, if you remember, right, so they will be like this. This is source, right? And if they are coming inside, these are called sinks. Okay, so if you, all these are streamlines only, so they are intersecting there. So here, theoretically, the velocity at the center is infinite, and that is called a singular point. Velocity infinite. Stagnation point, velocity 0. Okay, so these 2 are the special cases where the streamlines intersect, but anywhere else it cannot intersect because it cannot go in 2 directions at the same time. So because velocity should be in the direction of streamline. Okay. So
Excuse me, sir.
yes.
Sir, can you please explain again how at stagnation point, where is the other streamline? Like,
Yeah, this itself is one streamline. This is another streamline.
okay, the surface is one streamline.
Yeah, yes. On the surface also it is a streamline only. Because it is a wall, right? It is also acts like a streamline.
Okay, sir.
Okay, right. So these are the special cases.
Sir,
Yes.
sir, why pressure and velocity relate inversely?
Yeah, because okay, if you P by rho plus V square by 2 is equal to constant, or plus GZ is equal to constant, right? This is Bernoulli's equation. Am I right?
Yes, sir. Yes, sir.
Yeah. So if this is negligible, P by rho plus V square by 2, if one increase, another decrease because it is constant.
Yes, sir. Yes, sir.
Incompressible means rho constant, density is constant. So P plus rho, right? Is it
Yes,
clear now?
Yes, sir. Yes, sir.
Yeah, yeah. So that is they are inversely related in incompressible flow. Okay. So a compressible flow, rho also acts. So that's why it is difficult to say. We will discuss in detail when I talk about some nozzle or something. Okay. And so we have talked about the flow net and all. And another important thing is here. This is okay. U is equal to psi y, v equal to minus psi x, and u equal to phi x, v equal to phi y. Okay. So we got del dot v as dou u by dou x plus dou v by dou y equal to 0. Omega z dou v by dou x minus dou u by dou y equal to 0. Okay. So here, this is for incompressible. This is for irrotational. because we are considering a case where 2D incompressible and irrotational. Okay, psi has to satisfy this and phi has to satisfy this. So if you substitute here ux plus vy, u equal to phi x and v equal to phi y, what is that I will get?
Laplacian phi equal
Yeah,
to 0.
we get phi xx, right? Because u is phi x, it will become phi xx, and v is equal to phi y, so plus phi yy equal to 0, or del square phi equal to 0. Dou square phi by dou x square plus dou square phi by dou y square equal to 0. In the same way, if I substitute u equal to psi y here and v equal to minus psi x here, so we will get minus psi xx minus psi yy equal to 0. Okay, so if I make it plus del square psi is 0. So this is also Laplacian equation. So for 2D incompressible irrotational flow, psi and phi satisfy Laplace equation. Okay, so del square phi or del square psi, these are just second order linear partial differential equation. Okay, so it is very easy to solve this problem. So if I take flow over a cylinder and solve this, okay, I can get the streamline pattern. Because I can solve psi and phi, right? So if I know psi everywhere, I can find out where psi is constant. Those lines I can draw. So these can be drawn. And so once I know streamlines, okay, I know psi. So because of that, I can find out u and v velocities. And because of this, I can find out pressure from Bernard's equation. So I can find out what is the pressure distribution. As I told in the beginning, what I am interested in is to find out the forces coming onto the body, the lift force and drag force. So if I can find out what are all the pressure acting like this on this at different points on the cylinder. So if I want to find out the total force coming onto this, I can find out this. So what I do is, suppose I take a line like this, I find out what is the integral of the pressure over this. I can get what is the vertical force acting downwards. In the same way, vertical force acting upwards, right? And if there is a difference, there will be net lift force will be acting. But because of symmetry, both are same, and so there is no vertical force, that is called lift is 0. Okay, so force normal to the streamline or normal to the direction of velocity is equal to lift. Force in the direction of velocity is equal to drag. So here uniform flow is coming this way. So the force in this horizontal direction is drag and force in the vertical direction is the lift. In the same way, if I take a vertical line, the integral of this, if I take, I can get the force acting this way, and integral of this force acting this way. But because it is symmetrical, this is also 0. Okay, this is what is called as D'Alembert's paradox. I have told
Sir, I cannot
this
understand.
the people. Yes.
Sir, I cannot understand this.
Yes, sir. Can you please, sir, explain it once again, sir?
Okay, so I know all the pressure distribution over the cylinder, right? So if I take a central line like this, if I integrate all the pressure over the top surface, I can get the net vertical force acting. It will be downwards. And similarly for this, it will be acting this way. So net force, if I find out, if they are same, there is no left vertical force, that is 0. Is it okay?
Yes, sir.
In the same way, if I want to find out the force acting in the direction of flow, I take this surface, I integrate all the velocities in the here on this surface, I get, that is horizontal components. Okay, so net horizontal force acting in this direction and net horizontal force acting in this direction, both will be same because of the symmetry, and so drag equal to 0. So which says that a infinitely long cylinder, this is infinitely long cylinder. That's why I take it as 2D. kept in a uniform flow will experience zero force. Net force equal to 0. So this is what is called as theoretical or analytical analysis. This is actually this science is called as hydrodynamics. Hydrodynamics.
Sir,
Yes.
if the flow is non-uniform, then we
Yeah,
can
yeah.
expect
Then there will be difference in the force. There will be net force will be acting.
that is expect a lift and drag.
Yeah, yeah. We have to expect lift and drag. Okay. So this is this science theoretical fluid mechanics is called the hydrodynamics, and similarly, so the experimental people which developed what is the science called as hydraulics. Okay, so hydraulics and hydrodynamics, there are scientists working there and scientists working here. So there is always mismatch. And hydraulics people said, how can there be no force when a body is kept in a flow? It actually acts some force on that. We are saying no force. Okay, so the problem came. Actually, then they are working independently, but in 1904, Prandtl has come and developed boundary layer theory. And he said there is viscosity, right? So you cannot assume it is inviscid flow, though it is inviscid everywhere here, but near to the cylinder, right? Near to the solid, there is what is called as no slip condition because of viscosity. Okay, so there is a boundary layer acting here. There is zero velocity here, and within very small few mm, so there will be free stream velocity. So where I will have boundary layer. In the boundary layer, dou u by dou y is large. So because tau is equal to mu dou u by dou y, right? Though this is small, this is large. So tau cannot be neglected. Okay, so what he told is because of viscosity, what happens is if there is no viscosity, the velocity is 0 here, here velocity maximum, and here there is velocity 0. And so it gets accelerated here. This is called as favorable pressure gradient because pressure is decreasing. Okay, so dP is less than 0. So if pressure is less, we call it as favorable pressure gradient. It supports the flow. And from here to here, there will be deceleration.
Adverse.
This is adverse pressure gradient. Okay, so it accelerates up to here, and then there is sufficient momentum is there. Because of this, it overcomes the pressure and it comes here. That's what people thought, theoretical people. But actually, what happens is experimental people that it will not come like that. So Prandtl has modified the Navier-Stokes equations with viscosity. That is, del square psi, del square phi will not work. I have to consider viscosity. So here what happened? So because of the viscosity, there will not be sufficient velocity accelerated because of the viscosity. What happens? The low velocity fluid layers will try to drag the fast velocity layers, and there will not be sufficient thing here. So there will not be sufficient inertia to overcome the pressure gradient, and it gets separated like this. And so we got what is called as conformal vortex street. And because of this, there will be wake, and this is low pressure region. All right. So because here there is high pressure, and there will be net force acting in this direction, and there is drag. And similarly, the vertical symmetry also is lost because there will be vortices coming alternatively. There will be sometimes force coming downwards, sometimes force coming upwards. And because of this, there will be vibration or oscillation in the cylinder. Okay, so we have talked about this in about the failure of that bridge and all, and even there is what is called as humming of electric or telephone wires. So if you stand nearby a electric pole or a telephone pole, and if you keep your ears there, you will see a humming sound. So because air is passing over the wires, which are infinitely long cylinders like things, so there will be vortex street will be happening, and because of there will be vibrations of the wires, and it will give humming sound. Okay, so that is because of one carbon vortex street. Okay, so from here onwards, the fluid mechanics has fast developed, right? Because the experimental people and theoretical people joined together, and hydrodynamics plus hydraulics happened, and there is a fast growth in the fluid mechanics. Okay, so this is about a little bit history about that, and now we'll go to the governing equations.
Excuse me, sir.
Also, yes,
So you mentioned the term D'Alembert paradox. So
yeah.
was that the paradox that
Okay, why
just
paradox means though there is force acting on that, it gives that there is no force acting on that. So it is a paradox, right? So sometimes which seems to be right, may be wrong, may be wrong, may be right, like that. That is called as paradox.
okay,
Sir,
sir?
Yes,
that paradox was solved in 2004, sir.
1904,
Two-
2004. That
Yes,
is
sir.
recently.
No, sir. Yes, sir. Recently, they showed that for a viscid flow around a cylinder, the drag force will be zero.
That is long back, even before 1800s itself, they found it.
No,
That
sir.
is for inviscid,
Actually,
for inviscid flow, it is zero only. Okay, but they thought, people thought real flow is also inviscid.
okay, sir.
Okay, and that's why they told it is zero, even for real flows.
Okay, sir. Okay, sir.
So these are conservation equations. So here there are different ways of looking at a system. Okay, so we have seen that system is nothing but it is a quantity of matter on which we pay our attention. So what the kind of matter or how we can select the system. Okay, so based on that we have different types of models. We have 4 models. So one is anyhow we know closed system, and another is open system. This closed system is called as Lagrangian system, and open system is called as Eulerian system. Okay, so this is a fixed mass system. This is a fixed mass, and this is a fixed volume. Okay, and we get what are called as the equations that we get are called non-conservative form of equations. We will discuss in detail later. And Eulerian system gives conservation for conservative form of equation. Okay, and here we can again there are 2 different ways. We can take finite as a infinitesimal element. Okay, finite system or infinitesimal system. And here also we can take finite system or infinitesimal system. So these are the 4 models we are going to discuss. Okay, so here and the previous one. So this is a closed system. This is called a system approach. This is Eulerian system. This is control volume approach. So here, first, according to the book, I will take in that particular order. So Eulerian system, if I take, means open system. Okay, so that is we take control volume, and we can take finite control volume. Finite control volume means something like this. So there is a flow here taking place in this way, and in that a fixed volume I am focusing on, fixed finite volume. In the same way, infinitesimal element I can consider something like this. And here also the flow is taking place. Again, a small fixed volume I concentrate on. Similarly, I have Lagrangian system or constant mass system. This is fixed mass or closed system. And again, if I take a finite volume like this, so what happens is actually this moves with the flow, because some particles are there and these particles I am concentrating on, same mass. So the mass also moves with the fluid, and it can be infinitesimal small element also. So the element also moves with the fluid. Okay, so there will not be mass of flow crossing the system. Okay, so that because it is a closed system. Okay, these are the different ways of looking at it. And so if I try to find out the conservation of mass, or continuity equation. Okay, so here, because some mass is entering and some mass is leaving, right? So there will be change of mass within that. So there will be rate of change of mass, okay, is equal to whatever mass leaving the system. Okay. So here, if I take a small element here and then we integrate it. So here this is dV. So the mass is rho dV of and if I integrate it over the whole volume, okay, and so this is rate of change of mass within the control volume. Okay, this is rate of change of mass within the control volume is equal to whatever mass leaving the system. Okay, suppose this small element, if velocity going out is like this, and if unit normal is dA here, so for the small area, unit normal is dA. So here, V dot dA is the volume leaving the system. Okay, so why V dot dA? Area into velocity, component of velocity normal to the area. Okay, so suppose something, some area is there. So whatever area into the normal component of velocity I have to take. So the normal component you will get by dot product. Okay, into rho gives the mass. So this is the mass, and so here this is equal to mass leaving the system. And so here, if you take this side, so dou by dou t rho dV minus this is over the area rho v d dot dA is equal to 0. This is the continuity equation based on this particular model. Okay, and similarly, if I take this particular one closed system, actually the again, if I take this small element like this, so here rho dV is the mass of that small one, and because it is moving, both local and convective derivatives I have to consider. So d by dt of the mass is equal to 0 over this is volume integral like this. And coming to the infinitesimal element, This is the way normally you do in your BTech. So what we do is, I will do in the next slide. Like this. So here in X direction I will take. Okay, so some mass is entering and some mass is leaving in the X direction. So how much mass is entering in this direction? So U into, if I take this as dx and this is dy and this is dz. Okay, and so U into area normal to the velocity component. So what is the area?
dy into dz.
dy dz. So dy dz. Okay, into rho. So this is the mass entering the system in the x direction. Okay, so mass leaving will be, so rho u plus, because rho is changing and u is changing, dou of rho u by, so what is the change in the x direction for x distance tx? Okay, this is the thing. This is the volume leaving into dy. Okay, so this is the mass leaving the system in x direction. So what is the net mass leaving the system in the x direction? This minus this. So we will get dou of rho u by dou x dx dy dz. In the same way, if you take the mass leaving in the y direction and z direction, we are going to get dou of rho v by dou y dx dy dz and dou of rho w by dou z dx dy dz. Okay, this is the total mass leaving the system. So because of that, what happens? The mass of the system will decrease. Okay, so what is the mass? Rho into dx dy dz. Isn't it? This is the mass of the element. Dx dy dz is the volume of the element into rho gives the mass of the element. So the rate of change of mass within the system, this will decrease. So minus. So this is the mass leaving the system is equal to the decrease of the mass within the system. And so if I divide by dx dy dz, so I am going to get dou rho by dou t plus dou of rho u by dou x plus dou of rho v by dou y plus dou of rho w by dou z equal to 0. This is the way. If you write in vector form, this will become dou rho by dou t plus del dot rho v is equal to 0. Okay, this is the continuity equation. So if I write this here, dou rho by dou t plus del dot rho v is equal to 0. And so the third one, this is again total change in the total change I will get d by dt of rate of change of mass within the system, rho dv is equal to 0. Okay, this is the way we get. These are the 4 different models. And so we get the continuity equation in different forms. But we know that it should be same. So we can actually prove that they are same. Okay, so here, if I take this d by dt of rho dv, because this is a fixed mass system, so d by dt can be taken inside. So if I take inside, I will get like this. And again, this is an arbitrary one. So the limits are of no consequence. If this is 0, internal one must be 0. And this we will get here like this, d by dt of rho dv equal to 0. Okay. And here if you take, okay, so if I take this as 3 and this as 4 and this as 1 and this as 2, so 3 equal to 4. And if I take this fourth one, so I can, it is like the product of 2 terms. I can write like this, rho d of dv by dt plus dv d rho by dt equal to 0. And dividing this by dv, I will get like this. Okay. And if I take this particular term, the rate of change of volume per unit volume like this.
Divergence P.
Yeah, divergence. Okay, this is del dot v. So we will get d rho by dt plus del dot v, rho del dot v equal to 0. Okay, so this is the one actually I will write here. This is also equal to d rho by dt plus rho del dot v equal to 0. So this is another form. And here d rho by dt, so like d by d, capital D by dt is dou by dou t plus v dot del operating on rho, right? We already know this, plus rho del dot v equal to 0. So we will get dou rho by dou t plus v dot del rho plus rho del dot v equal to 0. So this is nothing but dou rho by dou t plus del dot rho v equal to 0. So this is equal to the second one. Okay, it is easy to actually, this we will get actually u dou rho by dou x, one you will give, and rho dou u by dou x, you will get in another term, and combining these two, you are going to get dou of rho u by dou x. Like that you will get. Okay, or in the, suppose if I take the second term, the second one, dou rho by dou t plus del dot rho v equal to 0. It means dou rho by dou t plus dou of rho u by dou x plus dou of rho v by dou y plus dou of rho w by dou z equal to 0. And I can write this as plus rho dou u by dou x plus u dou rho by dou x. Like this, dou rho by v dou rho by dou y plus rho dou v by dou y. Like this you will get. So this will become v dot del of rho plus rho del of v. And again, if you combine these two, it will become d rho by dt plus rho del of v equal to 0. Like this. Okay, so 2 equal to 3, 3 equal to 4, and if you take, I want to show 1 equal to 2. The first one is dou by dou t and rho dv plus rho v dot dA. This is the first one, and here what we call, we use divergence theorem. So which converts surface integral to volume integral. So we will get dou by dou t rho dv plus this also becomes, so here this becomes del dot rho v d, like this. So divergence of this particular one I will get. Okay, and because again the volume is same volume, it is not changing with time, this can be taken inside, and both are volume integrals. I can combine these two, dou rho by dou t plus del dot rho v dv equal to 0. Because again it is an arbitrary volume, right? So it is true for any volume. So it is independent of the limits. So I will get dou rho by dou t plus del dot rho v equal to 0, which is equal to the second one. Okay, so this is the way I can show that all the models will give the same equations. Okay, so it depends on whether you want Lagrangian system or Eulerian system, whether it's small one infinitesimal element are like this. So here, one thing you can understand is, if I take finite volume, this gives me integral equations, which are used in finite element method and finite volume method. And the infinitesimal element will give me differential equation used in finite difference method. Okay, and so usually in our CMTE, we are interested in Eulerian system and differential form. Differential form. So we are interested in this particular equation, dou rho by dou t plus del dot rho v equal to 0. Okay, so this is important. And another thing, because the third, we get what is called as Reynolds transport theorem, because one is control volume and the third one is system, Lagrangian to Eulerian. I want to see the relation between these two. It will be written like this. This is called as Reynolds transport theorem, where n is any extensive property and eta is corresponding intensive property. So this is for system. Rate of change of any extensive property of the system is equal to the rate of change of property within the system plus the amount of property leaving the system. Okay, so this is what is called as F flux. F flux means flux leaving the system. It is due to the convective thing. Okay, and this is local change in the property. Okay, so this is conversion of a system equation into control volume equation, or because I am interested in open systems, control volume approach. So this is the way they are related. This is called as Reynolds transport theorem. Okay, so suppose n is mass, extensive property mass. So the corresponding intensive property is 1. Mass per unit mass is 1. So if you substitute there, dm by dt is equal to dou by dou t of rho dv plus rho v dot dx.
Sir, here V is relative velocity of the control volume.
Which one?
V n rho V dA.
This is velocity of the flow.
Okay, sir.
Okay, previously we got that, right? So sorry. So here, this one I have written.
Okay, sir.
Okay, so that is Reynolds transfer theorem. What is the advantage of Reynolds transfer theorem is we know the conservation equations for closed systems. So all conservation is suppose continuity. Continuity is nothing but dm by dt is equal to 0. The rate of change of mass is equal to 0. If I take momentum equation and I call it as linear momentum equation. So what it says is the rate of change of momentum is equal to the force, where P is equal to momentum. Okay, so which is equal to mg. And energy equation, so which is first law of thermodynamics. This is second law of Newton. So first law of thermodynamics, what it says, the rate of change of energy of the system is equal to the rate of heat transfer minus the rate of work transfer. Am I right? So this is E is total energy of the system. M into small e is internal energy you can take. So or the specific energy. Okay, this is specific energy. And sometimes actually 2a I will write momentum equation, angular momentum conservation. So this can be written as some dh by dt. Rate of change of angular momentum is
Torque.
Torque.
right, very good. Torque. Okay, so h is equal to, I will write it as m r cross v. Okay, so this is angular momentum. And similarly, I can write entropy balance from second law of thermodynamics. So ds by rate of change of entropy of the system, ds by dt. How can I write? Greater than or equal to q dot by t. This is Clausius inequality. So this is the statement of second law of thermodynamics. Am I right?
Yes.
Yes.
Okay. So these are all system equations. Okay, and all are extensive properties. This is extensive property, this is extensive property. All these are extensive properties. This can be used to control volumes. Okay, so that is the way it is done. Actually, if you check fluid mechanics by Fox and McDonald or Frank White, so if you have studied in better institutes, they will tell in this particular way, fashion. Okay. Okay, finally, so the continuity equation what we got is dou rho by dou t plus del dot rho v equal to 0, or dou rho by dou t plus dou of rho u by dou x plus dou of rho v by dou y plus dou of rho w by dou z equal to 0. So if it is a steady flow, then dou rho by dou t equal to 0. Okay. So if it is incompressible,
Rho constant.
rho constant, so dou rho by dou t is 0. And also in del dot rho v, rho can be taken out because it is a constant. Am I right? And this will become del dot v equal to 0. Clear?
Yes.
Yeah. So that's it. It happens, and so that's what we have seen. And in integral form, if you take integral rho v dot dA equal to 0 or this. And so if you take in integral form, if you take a nozzle flow, so rho AV is equal to constant. Okay. So if it is rho AV is equal to constant, rho AV is nothing but m dot, that is kgs per second. Rho is kgs per meter cube, A is meter square, and V is meters per second. So multiply, you will get kgs per second. So m dot is equal to constant, rho AV equal to constant. It is for any flow in integral form. Okay. And so if you take incompressible, then AV equal to constant. Okay. So if you have a nozzle flow and incompressible flow, so we can see that A and V are inversely related. If A increase like this, okay, so A increase, V decrease, and this is what is called as diffuser. Am I right?
Yes, sir.
And if I have like this, so A is decreasing, so V will be increasing, and so this is a nozzle. Okay, for incompressible flow. But for compressible flow, we cannot say like that because rho also is there. Okay, for compressible flow, rho AV is equal to constant. And so when do we say a flow is compressible?
Density
Mach number less than
Yeah, very good. Who is that?
Sandeep.
Yes?
Sandeep.
Sandeep. Okay, Sandeep, very good. So if Mach number is less than 0.3, right, it is considered to be incompressible. Why? Because above Mach number 0.3, the density changes will be dominant and you cannot neglect it. Okay, so Mach number is very important. And sometimes a liquid flow may be compressible, and normally people say air is compressible and water is incompressible, right? You cannot say like that. It depends on what are the pressures that are acting. If pressures are very high, like hydraulic press, oil, water, all those things are compressible. And if the pressures are very less, even if air is there, it will act as if it is incompressible. Okay, if Mach number is less than 0.3, air also is considered to be incompressible. Am I clear about that?
Yes, sir.
Yeah. So if Mach number is greater than 0.3, then rho is important, not constant. So what happens is, if Mach number is greater than 0.3, rho is, and if mainly if m is greater than 1, in supersonic flow, the density changes are so high. Okay, so if I take a case of nozzle like this, so because the Mach numbers are very high, the change in density is very large. And so previously what we are thinking, if V increase, A decrease. But if V increases, right, density changes a lot, and this acts like a diffuser instead of nozzle. Okay, here A is decreasing, but rho, because it is very much increasing, V also decrease. Am I clear? In rho AV, A is decreasing. Because of that, you think that V will increase, but rho increases a lot. So because of that, V decrease, because rho AV is constant. So
Sir?
exponent one, yes.
Sir, what is Mach number?
Now, okay. Mach number is velocity of the flow by sonic velocity. This is sonic velocity. This is flow velocity. Okay.
Sir, what is sonic velocity?
Sonic velocity, sound velocity.
Okay, sir.
Okay, mathematics person. Who is that?
Yes, sir. I'm Krishnanda.
Okay. Right. So this is sound velocity. So for a given temperature, sound velocity remain constant, and sound velocity A is equal to root gamma RT. Gamma is ratio of specific heats, Cp by Cv. R is characteristic gas constant. T is local temperature. Okay, so based on the temperature, the sonic velocity, sound velocity can be calculated A is equal to root gamma RT. So here this is local velocity. Okay, so that is the way. And similarly, yes.
So this the condition that Mach number should be less than 0.3. We are just talking about the air. Huh?
No. It can be any flow, whether it is air or liquid. If Mach number is less than 0.3, any flow is can be considered as incompressible, whatever be the working fluid.
Okay.
Okay, so air also acts like incompressible. For most of the cases, suppose you take a very fast moving car in a air. So whether air acts like compressible or incompressible, so we don't know. We have to find out. Suppose it is going with, okay, so some velocity is, suppose very fast it is going 100 kmph. Okay, so 100 kmph means what is the velocity in meters per second?
27.78.
27.78
meter per second.
Okay, so meters per second. And what is the sonic velocity normally?
330.
330 meter per second. So if you see Mach number, it will be 27.78 by 330. How much it comes to?
0.08.
0.0 something, okay, or less than 0.1. So even if it is going with 100 kmph and the air as if it is blasting on that, but still the compressible effects are very much negligible. Okay, so what is the advantage when I do solve the equations? Rho can be considered to be constant. If rho is constant, one equation gets reduced. Am I right?
Yes, sir.
So by assuming some things, we are making the equation simpler to solve. Okay, so if rho is constant, one of the equation gets reduced and it is easy to solve the equations. Okay, so that is the advantage.
Sir?
Yes.
So the formula of speed of sound is gamma RT, like root over gamma RT. It is valid for adiabatic process, right? Or it's valid for...
Anywhere.
Okay.
It is not a process. At a particular point, you want to find out what is the sonic velocity at a given instant or at a point. So at that point, you know what is the temperature.
Okay.
Okay, so it depends on the temperature of the local point. Okay, it changes from point to point because if temperature is varying in the fluid, so the local velocity or sonic velocity also changes. Okay. Okay, that is about this. So that's why in supersonic velocity, a convergent one is a diffuser and divergent one is a nozzle. So surprising. So normal common man will think that a nozzle should be convergent. Am I right? But because normally we see subsonic velocities only. Supersonic velocities normally go down. Suppose if you see, if I want to increase velocity from subsonic to supersonic, okay, so initially I have subsonic velocity, and if I want to increase the velocity, what happens? Which nozzle I have to use? I have to use a convergent one because it is subsonic. But it goes up to sonic only. Maximum it can increase up to sonic only. After sonic velocity, if I want to increase further, this type of nozzle is needed like this. So if I want it to be smooth, I have to use what is called as convergent divergent nozzle. I have to use convergent divergent nozzle. And if you see a rocket from very far, suppose, okay, if somebody asks you to draw a rocket, normally people draw like this. Am I right? If you see from far, you will see nozzles like this. Okay, so what is the shape? These are nozzles only, we know. What is the shape of it?
Convergent divergent nozzle.
But it seems to be divergent, isn't it?
Yes, sir.
Actually, they are convergent divergent. It will be something like this. Okay, convergent portion is very small, divergent portion is very large. To reduce the losses, when the divergence portion always have a limitation over the divergence, otherwise there will be flow separation and all. Okay, so that's why it will be like this. So it is actually convergent divergent, not divergent. Okay, because convergent portion is very small, from a distance you don't see that portion, you will see as if it is a divergent nozzle. Am I clear?
Yes, sir.
Yeah. Okay, this is about the continuity equation. I think I'll stop here. So momentum equation we will do in the next class. This is the actual Navier-Stokes equation, which we will derive in the next class. Any doubts? And okay, and today 6 to 7 is the minor one.
So can you please tell the format of the text?
Yeah. It is all multiple choice questions. But there are many 132 questions are there. And it is only multiple choice, no calculations. Okay, just you have to take ABCD like that. You have to select it. That's all. Okay, one by one you will get the question. Some noise is coming from somebody. Please mute it. Okay, so there will be one by one you will be getting the questions. You have to answer it. And don't think that the time is not sufficient. It will take very less time. Even half an hour will be sufficient for this. I used to conduct with 100 questions with 20 minutes, but they are fill in the blanks. I used to conduct like that. But this is a multiple choice question. You need not write also. It is just clicking only. So you can do it easily. And so this is the way it will be. It's 6 to 7. So you have to be careful about the time. You have to, because automatically it will be submitted. Okay, by 7 o'clock it will be stopped automatically. Am I clear?
Okay, sir.
Okay. It is actually just I want to, and for the people who are new, okay, so they may be feeling we don't know, we missed the classes, previous classes, we may not have time. Don't worry, your whatever fluid mechanics you know, and whatever some common sense questions are there, some fluid mechanics which you have prepared also, they are sufficient for that exam. There will not be much preparation needed. Okay, so, and don't worry, it is a relative grading thing. So if it is tough or if there is no time, it will be same for everybody. Okay, don't complain about that time is not sufficient or more number of questions, anything. It is just to make you understand, to recollect all the things, and to feel comfortable and confident in the subject.
So basically, it's from the fluid mechanics part only, like kinematics, statics, dynamics,
Yeah.
physics.
What is that?
So will there be calculations like?
No calculations, absolutely no calculations. Only clicking only. You need not take pen.
Okay, sir.
Okay.
Sir, any multiple answer type questions, sir?
ABCD, like whatever gate or somewhere you will done that type of JE, anything, right? It is just ABCD, you will be there, you have to tick it, or you have to choose it. I don't know exactly how you do it. You have to choose the right answer.
Yes, sir. I'm asking if a single
Yes.
question has multiple answers.
No, nothing like that. There is nothing to worry about that. Only one answer, right? So there is no multiple answers.
Okay, sir. Thank you.
Right? There is nothing much to think. If you know the answer, you know it. Otherwise, you will not know also. Right? Just go to the next question and answer it like that quickly.
Sir,
right?
So
Yes.
can we get back, sir, to the previous question?
No, you will not get it. That is the problem in LMS. It is sequential. We call it a sequential. Once you leave the question, you will not get the question back.
So after opening the LMS, like in the in your section only, say it will be there in the like subject. That
Yeah,
is
you have to
CMTE.
go to LMS in my subject. You will see first minor. So you have to just go into that.
Okay, sir. Got it.
Okay.
Uh,
Yes.
is it any negative marking?
No, 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 nothing. No negative marking, no calculation, no multiple answers, nothing. Just to see, click it, go to the next, go to the next one, just like that. Okay.
So
Click it. Yes.
like the after minors, like after these minor,
Yeah.
uh, the remaining minors will be in, like the same type, or they can be calculations.
Mostly I will try to be like this, and I may give small problems or small derivation or whatever it is, because to make my, actually this, making this paper will take me 3 days or 4 days. Making question paper is difficult, but correction it will do automatically. That reduces my time. But if I give you a writing paper, I have to go through each person's answers and I have to correct it. So yeah, setting will be easier and correction will be difficult for me. Yeah, I don't know. Till now, I didn't plan it for the next minor how it should be. We will see. We will discuss. Okay, we'll see the story then. It is about the great Einstein. Just a few lines we'll see. So it is many people don't know about Einstein's background and the way how we know that he's a successful man, he's a Nobel laureate, and he's a great person like that. But what type of still I didn't cover some of the portion of the Einstein's childhood life. He's considered to be a retarded child by the many people in the family and school also. For 4 years or 6 years, I think he didn't speak, right? He is not able to talk up to 4 to 6 years. So he is considered to be mentally retarded, actually. So such a person, and okay, leaving about his childhood, upon his graduation from the Swiss Polytechnic Institute, Einstein hit his first road bump in his adult life. He was 21, unemployed. There, the people start working at very young age, right? Here, till you complete your graduation, post graduation, also people will look after you. Okay, so he was 21, unemployed, and had no idea what path to follow. His reputation as a student was in tatters from his mediocre schoolwork and his tendency to skip out on classes, meaning many of his teachers did not chomp at the bit to give him a job opportunity academically either. So in whichever way, even teachers also didn't support him because he's a mediocre student. As a result, to get by in life, he had to work several jobs just to survive. So such a adult life he has. And around this time, Albert's father passed away, and he passed thinking of his son as a complete failure in life. This knowledge of his father's thinking left Albert absolutely heartbroken. And later into his adult life, Albert had to divorce his wife and lose access to his kids just to focus on what he believed in, his work. He was hell-bent on proving that light can indeed bend, which of course many other academicians felt he was delusional for his thinking. And we know that light travels in straight lines, but he says light bends, okay, because of actually gravitational pull. So without any family and with the stress of his work piling on, Einstein began to fall ill both mentally and physically. This was not timed well too, with his work having to be put on the back burner due to the beginning of World War II. So he could not publish it also. Being a German Jew left Einstein in constant fear for his life. At the time of Hitler, these Jews are killed very many people, right? So he was always a threat for his life and survival too during this time, meaning there was little time to relax whilst not working. So that is the way his childhood, adulthood was. You cannot expect, if your life is like that, you will tell, "Wow, how can you expect something big from me?" Eventually, Albert Einstein would go on to achieve and success in the scientific field and finally get to the stage of proving his doubters wrong. He would go on to prove that gravity is a pushing force instead of being previously considered a pulling force. As well as this, he would go on to be the man to answer the question in regard to why the sky is blue and what decides this in 1910. He concluded that the phenomena was to be known as critical opalescence, and it is proved that this effect is caused by the scattering of the light in the sky's atmosphere, where individual molecules are splitting. This is what led to the discovery of the reasoning of the sky being blue. And to further his reputation even further, Einstein would eventually receive one of the highest and most prestigious awards possible when he won the Nobel Prize in 1921 for his paper that determined the light was merely a collection of particles. So what is the theory called as? For which he got the Nobel Prize?
Theory of relativity.
No. It is not theory of relativity. It is not general theory of relativity or special theory of relativity. It is not E equal to mc square also. What is the other contribution? It is photoelectric effect. Right? For that he got the Nobel Prize.
Yes.
So that he says light was merely a collection of particles. Okay, so this discovery from Einstein opened up an entirely new avenue. So the quantum mechanics, that is one of the fundamental paper. Okay, avenue for his fellow academicians and the world of science in the field of quantum physics to paths and ideas that have previously been pushed away as delusional or were completely unexplored. So previously they thought he was dreaming and he is telling something nonsense. However, what most probably encapsulates Einstein's scientific and academic career and what he is still most known for today is his theory of relativity, or the idea that E equal to mc square. This discovery was what lit the scientific world alight in ways that Einstein never expected he could do. This discovery opened the broadened landscape of what previously was taught in the subject of physics as an academic and scientific level, despite the fact that it took a number of years of stress-induced work from Albert Einstein himself before his ideas and theories on the subject were recognized to be true by his fellow physicists. Okay, what are the lessons we can take from Albert Einstein's life? Never accept your current situation as permanence. Okay, nothing is permanent in life. That we have to understand. In Einstein's early life, he could have easily played a victim card and wallowed in his sorrows from his father's opinion of him and his eventual passing, along with his professional and financial positioning, and he found himself in following his graduation, but instead he strove for something more than what he had become known as during his years as a student. He never allowed this situation to be seen as a situation of permanence, and always thought that at some point he could change the path he had ended up in is better. This is something we could all take from Einstein's life. When things are not going our way or our plans do not unfold how we previously would have expected. So that is an important thing. And follow your beliefs. Einstein lost so much at the hands of following what he believed to be true. He gave up everything he had in life on the path to prove what his heart felt was right. Because his beliefs are completely against what the world has believed. He had been labeled delusional and brushed away by his fellow academicians for his theories and ideas. And that despite this, he never gave up on these ideas and set out on the path to prove his ideas to be true, to show it in the face of those who once tried to deter him from what he knew to be true. This is something we could all use in life when we consider giving up due to the opinion or judgment of our peers. Normally, when all people say you are wrong or you are mistaken like that, so we normally leave the idea and go into their path. So overall, Einstein was a man who faced many curveballs that were being thrown at him on his path to success. However, he decided that these curveballs, no matter how hard they hit him, he would recover from the blow. He never let his early adult life and the opinions of those around him at that time defining him, as he went on to achieve so much in the scientific and academic landscape. His overcoming of the trials and tribulations of his path to glory are all stories that we can take and learn the lessons from on our own path to pursue what we feel is right in our lives. And thus, this is why Albert Einstein is still one of the most successful and academically praised people to ever live. Okay, thank you very much. Thank you and wish you all the best.
Thank you so much, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, thank you. See you.
Thank you, sir.
Thank you.
Hello, sir.
Yes.
Sir, I have a question, sir.
Yeah. Ayan, you
So,
tell.
yes, sir. What is the use of this equation that we are learning today?
I told you what is the purpose of CFD or CMTE from the beginning, right? We want to solve the fluid flow.
Numerical
Solving
equation.
fluid flow means we have to find out the parameters in the whole domain.
But it is
Why do
solved
you?
by computer, no, sir.
Yes.
The equation. It is the solve. The governing equation is solved by computer, no?
Yeah, yeah.
Then
Then
we are what we are.
see, our purpose is to solve the equations, get the flow field, solve the flow field, and find out what are the forces acting on the bodies. And you have to design the system based on what are the stresses are acting on that.
Okay, okay.
Isn't it?
Understood. Yes, sir.
Is it clear? Okay.
Yes, sir. It is clear.
Satisfied?
Yes, sir. Thank
Yeah.
you, sir.
Okay.
Yes, sir.
Thank you, sir.
Thank you.